Hey guys, thanks for checking in again with this oh so exciting video clip. Just kidding, but still, we want to learn chemistry, we want to do well. Um, Another topic that within kinetics that chemists study pertains to how we are imagining a step-by-step collision or a step-by-step collision decomposition combination might occur in order to reach a final end result. And sometimes there are two, sometimes there are three steps. Each of those steps that go toward an overall story, overall reaction, is called an elementary step. So I'm imagining this is something someone's proposed. They're imagining that possibly in the H2O2 decomposition that it does this and then does this and then does this. Let's look at it in a little more detail. H2O2, a molecule, we're imagining it breaks up or decomposes into two OHs, kind of a rare species. Doesn't last long. Then that one of those OHs collides with another H2O2 molecule, creating an H2O and an HO2, also a very rare species. But that doesn't last long either. That collides with another OH, creating H2O and water. And at some point it might be nice to draw pictures of these and imagine how the bonds are broken, bonds are formed, what the rearrangement might look like. But in any case, fast and slow. Now there's only one reason why we care about what's slow, because the overall process can only go as fast as the slowest elementary step. I rewrote those again here. And a plus sign to say, do you see what could possibly cancel? Is there something on the left of the arrow that's just exactly the same as the right of the arrow? In a way, this is similar to a process we went through when we played with Hess's law, but we don't have any heats here, any enthalpies. Oh, I see something. These OHs, and those OHs. Anything else? Oh, here's an HO2 and an HO2. Those will cancel. So indeed, that's what I did. Draw little lines through them, just one line so you can see what you canceled in case you made a mistake, in case you realize you make a mistake later. But the overall reaction is two H2O2s create two waters and one O2. This is called verifying those proposed steps sum to give the overall reaction. This HO2 is called an intermediate. It occurs here and here but does not occur in the overall reaction. Same story for the OH molecule. It occurs here and here, but cancels and does not appear here. So if I wanted to try to measure any of that, it would be extremely difficult to do. Very hard. So again, why do I care about the slow step? The slow step is what basically predicts the rate. Oops, wrong way. Excuse me, I say if I know which step is slow, then I'm allowed to do something which contradicts a rule we mentioned just a little while ago. But let me not point out the contradiction right the minute. Let me just tell you what the rule is. If and only if this is an elementary step, a single decomposition, a single collision, or a single simple change in some way, then here's what I can do. Since there is only one reactant right here, then I am allowed to say for this elementary step, which seems kind of weird and again contradictory, that my rate for the overall reaction, for this overall reaction right there, should depend on the slow step, which only depends on one of those molecules. And so I'm going to say one of those molecules, one of these molecules. That's really weird. So we want to focus on the slow step if we know a series of steps, a series of elementary steps. Here's another silly example. If this occurs, I don't know how silly it is, but I think it's a realistic example. If this occurs as a single elementary step, which actually is hard to believe, look at it. Two NO molecules, one Cl2 molecule, all come in together simultaneously in the same place at the same time to do this in one step. I am going to vote for that being unlikely. Seems pretty unlikely, because you're looking for three things to come together in the correct orientation with enough energy to make it happen. But if it did, and that's a big if, underlined, big F, in a single elementary step, then I have two NOs and one Cl2. So I focus on the reactants in the elementary step But if it's not an elementary step, you cannot do that. So again, I focused on those two and that one in this slow, no, my bad. This is just a single elementary step. So I'm saying you are allowed to do this if and only if it's an elementary step. 2 NOs, 1 Cl2, 2 NOs, so that's to the second order, Cl2, first order. Interesting. Now you're shaking your head probably right now saying, well, how come you contradicted yourself? Well, earlier we said you can't do that because usually an overall reaction has several different slow steps and you never can tell what the order of a particular reactant will be just by looking at the coefficient in front. Now we're telling you if it is an elementary step, then you are allowed to do that. Here's another process. Let's see, 2 NOs collide with each other. The warmer they are, the faster they collide, the more likely it is to go quickly, but I don't know. These two collide with each other, sticking together to give this in a fast equilibrium, fast back and forth. Then that N2O2 collides with an H2, and looks like the hydrogen, in some sense, acquires one of those oxygens to become water, creating the N2O molecule. Then the N2O molecule collides with another H2, and in a similar way, similar to what we did up here, creates another water molecule. Huh, interesting. Why do I care what's fast or very fast or slow? Well, I don't care what's fast or very fast. What I really care about is a slow step. That's what slows things down. So if this happened in an elementary step, well, I'm claiming this is an elementary step. Well, first of all, cancellations, N2O2, N2O2, N2O, N2O, nothing else cancels. 2 NOs, 2 H2s, 1 N2, 2 waters. There's the overall reaction. Just by looking at this, there's no way to tell what the order, what the rate law would be for this. But if I look up at the slow step, I see one of these and one of these. But there's a problem. And the problem is this. Well, here's the slow step. So I wrote to the first power and to the first power. Cool, no problem. But the problem is this. This N2O2 species, this thing right here, I could not really measure it easily in the beginning or the end because it's an intermediate. If we look back up here briefly, I see the N2O2 canceled here and here and doesn't occur here anywhere. So since this species is not really in my overall reaction, I cannot really include it and easily measure it in my overall rate law. So I've got to do this. And again, I said the problem is that the N2O2 is an intermediate, not appearing in the overall reaction. So I do a little substitution. This seems like another fish story I'm making up, but it's not. Where did the N2O2 come from? Well, this canceled from this right before it. This canceled from this. So in other words, this came from this in a fast equilibrium. So guess what I'm allowed to do? And you can prove this mathematically, but I don't want to. It takes too much time, and the numbers are too, in a way, confusing unless you study it for a much longer time period than we have. That I can just take this 2NO and substitute it into this and say that these two contribute to the second order and this contributes to the first order. I said we are allowed to substitute for this intermediate what it was. Typo, I'll fix that before I post it, I hope, if I get time. What it was that preceded it or created it in a preceding elementary step. So again, what I'm trying to say is, since this doesn't occur, this is the slow step. Look at the reactants in the slow step. If there's an intermediate, you should substitute in for it what produced it. And hopefully it's that simple, although sometimes it gets a little bit more messy than that. So originally I had written this, but now I'm saying that's an intermediate, so I should substitute in 2 NOs. And again, that's 2 NOs, 2 NOs. Those two go right there, or in other words, all together in one color. There's my predicted rate law based on the idea, the supposition, the hypothesis that this is a slow step. And also the supposition that those 3 elementary steps really do run in that order. Now the real test would be go into the lab and see if you could verify this and verify this. And if you could verify it, that this is second order, this is first order, then you might have a pretty good foundation to say that that proposed mechanism is really what's happening. All right, a proposed mechanism for the reaction. A2 plus B goes to 2AB. That's the overall reaction. We're going to imagine perhaps it happens in 2 steps, where an A2 breaks up into 2 A atoms, then an A atom hits a B atom, creates an AB. Hey, sorry about that little hiccup. I made a boo-boo. Had to go fix it. Now, a proposed mechanism for the reaction. A2 reacts with 2AB to give 2B to give 2AB. The overall reaction is this. I wonder if one A2 breaks apart into 2A molecules, or atoms, my bad, and then an A atom collides with a B atom to give an AB atom molecule. If we say that we observe in the laboratory a second order in A, first order in B, I wonder if this mechanism will jive with that. Again, I focus on the slow step. Whatever happens in the slow step, that's what determines everything. Again, sorry about that interruption. Gee whiz. Well, anyway, shoot. So the slow step. Yeah, that's what I want to focus on in a minute. And if you're really quick, you've already beaten me to the punch. If I'm second order in A2, well, I rephrased down here. Excuse me. If I have a slow step and a fast step, I thought initially maybe perhaps I should, to make everything work out, multiply everything times 2 here. 2 A's, 2 B's, 2 AB's. Let's see, what is it that cancels? Oh yeah, so if I have 2 A's over here and 2 A's over here, those will cancel, and my overall reaction looks like the mechanism would indeed give what I need. That's the result that I was looking for, but is this slow step consistent with what was observed? I said since the reactant species in the slow step determine the overall rate, and that's a slow step, I would write A2 to the first power. But lo and behold, that's not jiving with what we said a little while ago, that I had A to the second power and B to the first. So we better scrap that mechanism. These steps that we were looking at, there must be something wrong with them, or it must be more complicated than just that. So the observation kind of governs our theory. Here's one more. AB reacts with C to give ABC. They all stick together. Then a moment later, the ABC decomposes and spits out the A. The BC goes on to collide with another C, and that sticks together into a BC2. Well, if you're quick, you're already ahead of me. What's going to cancel? I see a whole bunch of intermediates, or 2 intermediates. ABC, ABC, and BC cancel, and my overall reaction. I wonder... Did I have a slow step? I didn't even label a slow step. Let's say this. If the observed rate law from data is this, excuse me, which of those steps must be the rate determining step? 1 AB and 1 C. 1 AB and 1 C. That's what I observe as, so AB to the first power and C to the first power. And look at my steps. Let's see, AB and C, no. AB and C, no. AB and C, aha. So I'm going to have to say, I'm going to have to bet, that one right there, that's a slow step. Hey, thanks again for watching, guys. See you in class.